How's it going, guys? I'm Aiden. I'm going to be showing how I do my astrophotography. So today we're going to go out to a dark site and take my telescope, my mount, and my tripod and my camera, and we're going to go take some astrophotos. So the drive out to the dark site is about 50 minutes from Omaha. It is near Weeping Water, Nebraska. It gets pretty dark there. We're gonna be around a class 4 Bortle dark sky scale. I left around 8 so that I could get there around 9 so that I still had a bit of light so that I could set up in the light. There was a road closure going towards Weeping Water, so I had to take a detour. This means I would have to set up in the dark, unfortunately. This is Weeping Water. It's a small town with a population of around 1,000, but the dark side is just outside of this area. This is the road to the dark site, and the Omaha Astronomical Society owns this land and lets people basically observe from it if you're an OAS member. When I got there, there was only a little bit of light to set up, but it will work. This is the mount's tripod, and that black notch points towards north. Here is the mount on the tripod and the counterweights. There's supposed to be an extension on that rod there to put the weights lower down and create more torque so that my heavy telescope can rotate easily without any wear on the gears that make the mount turn. This will pose a couple of problems that you'll see in the future. Some tracking errors, just because the mount has to work more than it should have to. Here's the telescope. It's on the mount. It is connected using that dovetail mount right there, and clamped down using those green knobs. So what you're seeing now is the process of balancing the telescope with the counterweights. I have to balance it on two different axes, the declination and the right ascension axes. Um, so yeah, this is where the counterweights would pose a problem. I was able to move the counterweights down further to create more weight on the counterweight side, which worked, but it's not ideal. Um, this would pose, yeah, a couple problems with the tracking in the final result. So now I'm putting on the camera. My camera has this adapter. It's a T-ring adapter, and basically you don't have any lens on it, and you just screw in the T-ring adapter, and you can attach it directly to the telescope, and you can see through the telescope with the camera. Here I'm balancing the right ascension, and as you can see, it's heavier on the telescope side, and that's just because of the counterweights aren't extended out further enough, but this should work. Here I'm plugging in the hand controller for the mount. This will allow me to star align and then slew to targets that I want to shoot. Here I'm plugging in the power cord for the mount. So now I'm ready to polar align. So there's basically an additional telescope running through the mount that allows for polar alignment. You basically line up Polaris on this dial according to the time, and it will pinpoint the actual rotation of axis of rotation of the sky. Here's me plugging in my equipment. I have two outlets for my mount and for my camera to run off of. Here's me plugging in my camera. I'm using this adapter that fits into the battery slot, and this makes it able to run off of power, like a stable source of power, instead of a battery, so I don't have to worry about batteries being charged. And there it is, like the light. So now I'm turning on the telescope, and you can see the remote turns on. It says initializing, and this will prompt me to enter in my information like latitude and longitude, time, and also if there's like daylight savings. After establishing a location, the mount will need to be polar aligned. So that's towards Polaris, and we need to line that up with the polar scope, which I'm showing right there. So now it's time to star align. You can either do a 1 star alignment, 2 star alignment, or 3 star alignment. At this time I'm doing a 2 star alignment, and then later in the night I do a 3 star alignment again because it got out of alignment. Here the remote wants us to 1 star align with the star Arcturus. Based on the location data we gave to the remote, it will calculate a lot of stars that are bright in the sky, that are in the sky at that time of night, and we'll do our alignment based off of those stars. Now that we press enter on Arcturus, the telescope will start slewing to where it thinks Arcturus is, and then we'll have to use the finder scope and the camera to actually pinpoint it, focus it, and center it on the camera, and then move on to the next star to complete our 2 star alignment. After finishing a bit, I was able to frame Arcturus on the center of my camera, and we'll use this star since it's bright enough. We'll use this star to focus and set our focus to do our imaging. To focus, we're using this contraption called a Batten-off mask, and basically what it does is creates a diffraction pattern that you're able to use to focus. Basically, there's spikes on the star you see there, and you're able to easily focus the star, basically making the spikes directly in the center to get a perfect focus. Next, I did the 2nd star, and it says it wants to go to Vega. So this would be the second brightest star in the sky at this point. And so we'll slew to it, and then we'll move the telescope around to frame it in the center of the camera again. And then we'll be ready to go to our target and start imaging. Our first target of the night is going to be M51. So you can see here the Messier catalog. I can put in 51 there, and then click enter, and it will slew to where it thinks the M51 is, based on the alignment stars that we gave it, that we framed up in the center of the camera. So it should slew right onto M51, but we'll probably have to do some framing. There's a moth. Yeah, so there's a lot of bugs out there, especially with the flashlight of the camera. So once we're on M51, we took a test shot. This is a 30-second exposure, the longest I can do without the intervalometer, at the highest ISO that I could. And you can see at the bottom of the frame is M51. So we'll have to do a bit of framing to get it in the center, and then start taking our exposures. This is the intervalometer. This is what we'll use to take those long exposures and those multiple exposures. I'll be able to click a button and walk away from the camera, and it will keep taking those exposures. And I think we're going to do 2 minutes exposure time tonight. So we actually did 3 minutes, and I know this because it took an hour to take the light images, and I know I took 20 of those pictures, so that's a total of 60 minutes of exposure time. But now, after taking those pictures, we're going to do our calibration frames. So first we're going to do the darks, and basically you put the lens cap on them, but I couldn't get it on, so I just put my sweatshirt over the telescope. And basically you take these calibration frames to get rid of as much noise as possible in the post-process phase. So after M51, I had a bit of fun. I went to a couple other galaxies like M101, and I took exposures of M101 and I stacked them together and did editing on them, which you'll see. But I also went to a couple other galaxies like M87, M81, and also the Ring Nebula. So yeah, the only nebula that night. So after we get back from taking our pictures, we can take a look at what we got. I put them into folders with M51 and M101 as our main ones, which we're gonna stack. So in M101 we have lights and darks. The lights are just the normal pictures, and then the darks are the calibration frames with the sweatshirt over what we did. So let's look at our lights. Okay, so now we can go through and see how we did, I guess. So you can look at the stars, and as I scroll through these pictures, you can see, oh, here we go, there's a satellite too. Um, but yeah, like you can look at the stars and like this one right here, you can see that the stars are really stretched out. If I can zoom in on one of these, it's like that. And that's because of the bad tracking, because the telescope wasn't balanced properly, because I wasn't able to. So we're gonna throw out some of these ones with the star trails, because they won't be good for stacking. Like you want a lot of pictures for stacking, but you want them to be accurate pictures. So we'll throw some of these out. Okay, now we can look through our M101 pictures. Go to our lights, and we can check these out. So as you can tell, there's like a lot more noise and a lot more like light pollution on these ones that we took. And I'm gonna check to see. I'm gonna look through and look at the stars for each one. These ones look alright. I want to see. This one looks not great. I might throw this one out. This one is 06. Let's check the rest. The rest look good. Yeah. So we gotta throw out. We gotta throw out one probably, and that one was 06. Yeah. Actually, I'll just keep it in. I'll keep it in just because we don't have a lot of them anyways. So we want to get as much as we can. But yeah. And if I remember correctly, the darks looked alright. Yeah. So. Yep. We're good on those. So now for the others, I just want to show you what I took and what like the capabilities of my telescope are. So this one was, I'm pretty sure this one was M87. This was M87 right here, and you can see like other galaxies. I can't tell if there's one up there, but yeah. So like I would be able to stretch this out and like see a bunch of galaxies because this is like a region in the sky where there are like a lot of brighter galaxies, I guess. So like moving around, you can see another galaxy right here. That isn't as much. There's another galaxy right there. So yeah, I'm not sure what this is. I think here's a nice satellite going through the frame. And here we go. So these I took the 3 pictures of the Ring Nebula. They all didn't turn out good. You can see this is probably the best one. Yeah, so that's the Ring Nebula. It's a planetary nebula. This was originally a star, but then exploded, and that's the remnants basically. The rest aren't as good. I think I hit my telescope or something, or yeah, something went wrong with the tracking. But yeah, as you can see, like heavy star trails. But yeah, and then I think I went back to M87. Oh, this might be a new galaxy. I'm not sure. I can't remember what I took. But yeah, this is one. And then I went to M81, which is Bode's galaxy, and this was like right about when like the clouds started rolling in. So all that light pollution reflects off the clouds and creates this sort of haze. Okay, so now we can start to stack our pictures of M51 and M101. Okay, to stack these pictures, we're going to use this software called Deep Sky Stacker. And you can basically put in the picture files, which are the lights, and then you can put in these calibration frames. I didn't take flats or biases just because running low on time, and darks are really what you want to get those dead pixels of the sensor out of those pictures. So what we're going to do is we're going to open up the picture files, and then we're going to go to our M51, our lights. Then we're going to select all of those and enter them in. And then we're going to check all. Yep, and then we're going to go to dark files, dark frames. Go to the darks. I only have 3 darks, but I think it should be fine. Should be able to do some editing. So now what we're going to do is we're going to register check pictures. We're going to calculate, so we're going to see like at a 10% star detection threshold, we're going to calculate like how many stars it will see, and they'll use these stars, or the software will use these stars to basically line up the pictures to get a perfect stack. So 80 stars is alright. I want to see if we can lower that a little bit, and that will like speed things up a bit. 62 stars is great. So we can go to, yep, so stack after registering, stack the best. We just want 100%, just so that it stacks all of our pictures. Yeah, we should be good. I think recommended settings. Yeah, this should be good. So we'll go ahead and stack these images. And sometimes, if you have a lot of images, it will take like upwards of like 1 or 2 hours if you don't have like a good computer. But since we don't have a lot of pictures, this shouldn't take that long. Okay, so it just finished stacking. And as you can see, it's quite a lot darker. And that's just because the data is squished in a little bit more, and that's what we're going to use Photoshop to stretch out that data and get some good get a good image out of it. Okay, so this is the output. It's a TIFF file, so it's completely uncompressed, and we can open this up with our Photoshop. So first things first, when we're in Photoshop, we're gonna do a crop because you can see these stacking artifacts. So since the tracking was off, the images create like an artifact, like it's like stacked on top of each other, but they had to move them over. So there's gonna be this black like line around it. So let's do a crop. Okay, so now that we did the crop, this is looking better. We're gonna duplicate this layer, so that we don't mess around like with this. We have a backup basically. Yeah, we don't want to make all these changes and then we can't revert them. So we want to have this backup. So we're gonna do our first stretch right now. So we're gonna go over to curves, and we're gonna go to this preset, and I have these arc sine curves. So I can do a 30, so arc sine 30, and this is just to preserve the colors. So if I was able to, or if I was just like stretched it and like did all different stuff to it, the color of the stars would get basically bloated, or the stars would get bloated. So after doing the stretch, we can go over here to layer and flatten image. So now we want to do a levels adjustment, and we want to raise this black point up to around about like right here. So now we can see the galaxy to start to come out more, but we can also see this gradient of light pollution in the background. It's not like completely black, and we'll edit that out in a bit. Okay, so we're going to do another stretch using our curves, and we can do arc sine 10, and I think let's go for arc sine 30. I don't know if that's going to do any more than we want it to. We can also stretch it later after we get rid of this gradient, all this light. So we'll do this and flatten an image. Create another duplicate layer, and then we want to do our levels again, and we want to bring that black point up like that, and to see all this data right here on this histogram, this is basically part of the gradient, all this junk. So to remove this gradient, we're going to draw around the galaxy, just because we don't want to lose out on any detail in the galaxy, and create a selection like that. And then what we're going to do is we're going to do select inverse, and then we're going to feather it. Feather the selection by, let's just go 10 pixels, and that will make the selection less harsh. So now what we'll do is come up to filter, and we're going to use, let me select that so that I can use that, and then we're going to go use this gradient and exterminator, and we're probably going to put the aggressiveness to high, but we can go medium or high. I think let's go medium first, and and medium detail, and we'll see how this works. See if it, yeah. So this does a lot to remove that kind of like hueish color from the light pollution. Yeah. So now we should be able to do another additional stretch, and get more of this galaxy. Okay, so now we're gonna do a levels adjustment, just because we got rid of all of that stuff on the histogram, and we're gonna put this black point up to here now. So now it makes the actual background more black. Um, so right now there's a lot of noise, right? We can't really get rid of right now. So I'm gonna bring up curves again, and we'll try to do another arc sine curve. Um, Stretch. Yeah, so all of this noise is just basically because we didn't get a lot of pictures, a lot of exposures, I guess. Um, and if you get a lot more exposures, the stacking program actually like averages out the noise, and that's how you get rid of the noise to get a better picture. But now you can see, doing the stretch, you can see a cool galaxy right here and another one right here. Um, and I'm debating if I should crop these out or just keep it like this. Okay, so we're gonna do this levels adjustment, bring this black pen up again. So now I'm gonna try to do an additional gradient remover and see if that helps with the noise, this color noise. Actually, first, what we're gonna try to do is use this camera raw filter, right? So we're gonna do a noise reduction, and we're gonna bring up this the luminance and the luminance detail, and I'm gonna see what these sliders do. I'm not entirely sure. There we go. So this color, this color is gonna greatly reduce this color noise in the background. So if we bring that up and we slide around the color detail, we don't want that a lot. Let me zoom out though, just to make sure that the yeah. So we don't want the galaxy to look all like blurry. So let's bring this down a bit. Okay, yeah, there we go. So we don't want to get rid of all that detail in the galaxy. So let's just do a little bit of luminance. Bring that up. Luminance contrast. Let's see. I don't think that does anything. It's not doing anything. Color. Let's bring that up. Yeah, just color noise, and yeah. So I think that's as best we can get right here. Bring down the noise a little bit, and now we're gonna do another gradient removal to see if that helps. And then we're gonna go to filter, gradient exterminator, and I think what we want to do is maybe just do let's do a medium again. We'll do a medium again and see how it does for this image. So yeah, so it brings out it brings down these color noises, and yeah, it's looking pretty good. I think I am good to call it here. Let's see if we can work out a crop for this image, just like this, so we can get these two galaxies in, because that looks pretty cool. So we do that, and yeah, I think this is the best we're gonna get, just because I can't really get oil of all that noise, and we still got this cool galaxy up here. The focus looks good, and the detail in M51 is really good. I could actually bring up what I got last time. Let me bring this up. This was a while back, like last year. So I think I bumped up the saturation, but yeah, it's pretty similar. We got more of this dust lane over here than last time, and yeah, I think definitely more detail in the galaxy right here. So I'm happy with that. So I think I'm good for this. So this was the imaging editing process of M51. I'm going to do M101 off camera, and I'll put them side by side and we can do a comparison. Now that I'm done editing, here's a quick overview of each galaxy, M51 and M101. For M51, the distance from Earth is 31 million light years. The apparent magnitude is 8.4, and apparent magnitude is on a reverse logarithmic scale. So the higher the number, the less bright that object is. As a reference, the moon is, I'm pretty sure, a negative 13 magnitude, around that area. So this is a pretty faint object in the sky. So the classification for M51 is a grand design spiral galaxy. So it's pretty standard spiral, um, kind of like the most common uh, type of spiral galaxy. So the features. So there is a dwarf galaxy called NGC 5195, which is this right here, and they're interacting. And I'm pretty sure that this galaxy passed through M51 around 500 to 600 million years ago. So yeah. So and then yeah, and also M51 is about 43% the size of the Milky Way galaxy. So small, reasonably smaller than the galaxy that we live in. So here's the Pinwheel Galaxy, and this is how much I got done editing this one. So the distance for the Pinwheel Galaxy is closer. It's 20 million light years away. The apparent magnitude is 7.9. So this means that the Pinwheel Galaxy is actually brighter than M51. I think it kind of shows up fainter just because of the lack of exposures that I did for this galaxy. So I think that's the reason why it kind of shows up a little bit more faint. So the classification for this galaxy is an intermediate spiral galaxy. So it's in between a barred spiral galaxy and a regular just spiral galaxy. So it's pretty symmetrical. Spiral galaxy, it's face on to the Milky Way, or to our, I guess, our observation, our Earth. So features of M101 is that it has a high density of H2 regions, and H2 regions are regions of high density of hydrogen, ionized hydrogen. So positively charged hydrogen ions. So a hydrogen with an electron stripped off of it. So in these H2 regions, they have a high rate of star formation, and so these little blobs of like kind of bluish, whitish regions. These are I'm pretty sure these are the H2 regions. It just doesn't show up as like a red color like we would expect with hydrogen, and that's just because my camera has a infrared blocker, and since like the red color it's like really close to infrared, and also hydrogen does I guess emit infrared light, and so it would show up more red if I didn't have that infrared blocker on the camera sensor. So the physics principles used in this demonstration were concave and flat mirrors, and this is a diagram of what my telescope looks like. It's a Newtonian reflector telescope. So in the back, this is the primary mirror. So light comes in from up here, and it bounces off of this concave mirror. So this is the primary concave mirror, and this is a parabolic mirror. So yeah, and then so it diverges like you would expect a concave mirror to do, but before it reaches the focal point and like flips over and has the image flipped like over here, between the focal point and the center of curvature, it gets reflected off of this flat mirror, which then puts the focal point over here, and that's where it's flipped, and where you see it, it's the image is flipped. So it's an inverted image with a virtual image over in this area, because you're looking at the mirror, and there's going to be the virtual image is around over here, because this is the flat mirror. So thank you for watching.